I would like to present a paper that we published this year with Professor Tampone.
Hi, everyone.
Hello, hello, and Dr. Jeb Ben Hamouda and Dr. Eric von Schwerin. And the title of our paper is a Lagrangian relaxation for continuous time optimal control of coupled hydrothermal power systems, including storage capacity and a cascade of hydropower systems with time delays. It will take me a few slides to jump into the actual mathematical formulation of our problem, so bear with me. Our study focuses on the power production system of a country, which is comprised of hydropower, fossil fuel stations, wind and solar power farms, and the battery. All of these sources provide electricity to the grid, which is then distributed to various consumers. And our goal is to construct an optimal schedule of operating such power system in a time frame of 1 day, so that the cost of power production is minimized and the country's demand is met. We study an actual real power production system, specifically the Uruguayan system. Uruguay has been a pioneer in the field of renewable energy, with 87% of its power being produced by the renewable sources in 2021. This has been made possible by the significant growth of the wind and solar power in the recent years. In fact, on some days, the demand of the whole country can be satisfied by the wind power. But these sources, the wind and the solar power, have very the variability of these sources on a time frame of 1 day is very high. So if we want to construct an optimal schedule for 24 hours, we need to account for this variability as close to the reality as possible. So we are working towards modeling the wind and the solar with SDEs, so that we will have a stochastic optimal control problem. And today I will present you the paper, which is the stepping stone towards this big stochastic optimal control of renewable energy project, where we work through the deterministic case. A very distinctive feature of our system is the time delays. And this happens because we have 3 dams built on the same river. And this is a situation that is very common throughout the world. In our case, we have 3 dams, Bonete, Baigore, and Palmar, and it takes 6 hours for the water to reach from Bonete to Baigore, and 10 hours for the water released from Baigore to reach Palmar. And in many works, these time delays are either not taking into account or set to 0 for simplicity. But you can see that 6 hours and 10 hours are a big portion of the day and can significantly impact the optimal schedule. I want to also outline what kind of solutions you can find in the literature and how our solution stands out. So many works focus on the discrete time approach, which leads to large-scale optimization problems, which are then solved by nonlinear programming methods, integer, mixed integer programming, and network flow algorithms, depending on the objective function. And I will tell you more about how the continuous time approach that we are using is advantageous later when I will talk about the results. We have found a few continuous time solutions, but they are very specific in the system that they analyze and are hard to generalize to a broader class of energy production systems. The time delays are considered only in a small number of works and only in discrete time setting. Usually only the small-scale systems are studied, like only hydropower systems or coupled hydrothermal and hydrowind systems. And we have not found any work that would also include the battery. Our approach to solving the power production scheduling problem is a continuous time approach, which allows for the extension of controls into the points off of the numerical grid by interpolating the derivatives of the value function obtained through solving the Hamilton-Jacobi Bellman equation. This means that potentially having one solution, we can have access to schedules with different time resolution. We incorporate Lagrangian relaxation to address time delays in the system, and we also include the battery in the system, which is very attractive for the operators because the batteries can significantly reduce the variability of power production through storing energy and redistributing it throughout the day. But numerically, it presents a lot of difficulties because batteries have fast dynamics compared to the other sources of the energy system. So like I said, our goal is to produce as much power as needed and as cheaply as possible. Here you see the demand in Uruguay in different seasons of the year, and this is the real data that we use in our simulations. We want to meet this demand by producing power with the dams, PH, the hydropower, the fossil fuel stations, PF, and the battery, PA. And now I will describe how we are modeling each of these power sources. Our model of the dams describes the state of the system through the volume of water in the dam V, which we can control through the turbine flow phi T and spillage phi S. Both the turbine flow and the spillage are functions of time and volume, and the dependence on volume is something that is related to the construction specifications of the dams. The power produced by the dam depends on the water that we turbine and spill, and also on the water difference, the upstream difference H capital and the downstream the upstream level of water H capital and the downstream level H. So on the one hand, the more water we turbine, the more power we produce. But on the other hand, the more water we turbine and spill, the more we raise this downstream water level, which reduces the power production. And the resulting function, which accounts for both of these counter effects, and the coefficients eta and d are something that can be calibrated from the data. And next, we consider the cost of power production, which is simply equal to the amount of water that we turbine and spill throughout the day and multiplied by the cost of water KH. And these coefficients KH represent the future value of the water, and they reflect the ability of the dam to substitute for the more expensive power sources like the fuel. They are usually the outputs of midterm optimization problems, and in our work are taken as input. Here you can see the dynamics of the dams, which we derive from the balance between the inflow of water and the outflow of water. There are two types of dams, connected and non-connected dams. And the dam is considered connected if it receives water from an upstream dam. In our case, it's Baigorria and Palmar. The inflow for these dams consists of the natural inflow I, like rainfall, and the water received from the upstream dam and released from that dam sometime in the past T minus tau. And the outflow is simply the water that we turbine and spill at current time. We also have physical constraints on the boundaries of the domain where the dams are either empty or full. And the non-connected dams, Bonnet, which is the first dam in the Cascade, and the Salto Grande, which is built on a different river. And the corresponding dynamics are similar, and they just don't include this water from the upstream dam terms. The modeling of the fossil fuel station is straightforward. We control the fossil fuel station with phi f, which is simply equal to the power that we produce. And the cost is equal to the power produced multiplied by the cost of fuel. In many works, you can find the unit commitment problem that also consider the startup costs as well as constraints on minimum up and down times. And this is something that we can consider in future work. In our system, we added the storage capacity, which we model by a single large battery. And we describe the state of the battery with the current charge A. We consider that there are no power losses when we're using the battery. There are no operational costs and no aging effects. And we control the battery with a power flux phi A. The negative value of phi A represents charging the battery, and the positive value represents supplying the energy from the battery to the grid. Okay, and now we can move to the mathematical formulation of our optimal control problem. So we want to minimize the cost of power production over here over the set of admissible controls A, given the system dynamics here, the flow constraints over here, and the power balance equation. The problem with this formulation is that we have the time delays in the dynamics, these red terms, so that we cannot apply a classical dynamic programming principle to associate an HJB equation to this objective function directly. We address this problem by formulating the dual problem using the Lagrangian relaxation. So we first introduce the virtual control psi at current time t, which is simply equal to the water turbine then spilled from an upstream dam sometime in the past. And the idea is to relax this constraint by adding it into the value function over here and penalize the violation of this constraint with the Lagrangian multipliers lambda. Yes, and then the dual problem will be formulated as maximize this new dual function theta of lambda. This approach allows us to have all the terms after some algebraic manipulations represented at current point in time t and not depend on the past. So instead of solving the initial primal problem with time delays, we are going to solve the dual problem without time delays and use that solution to construct the solution of the primal problem. The dual function is subject to similar dynamics and constraints where, like I said, all the terms are now given at current point in time, and we can apply the classical dynamic programming principle to associate an HJB equation for the dual function theta of lambda for a given lambda. And another advantage of such approach is that in this case, the dual problem will be a concave problem, and this will be very convenient in the optimization. The Lagrangian multipliers lambda are in general piecewise continuous functions. So this means that the dual problem will be an infinite dimensional optimization problem where one seeks to satisfy the constraints pointwise in time. Instead, what we're going to do, we will satisfy these constraints on average of lambda discretization intervals, which implies finite dimensional optimization. So we will approximate these Lagrangian multipliers with a sequence of piecewise constant functions, and we can control the quality of our approximation with the number of intervals in this time mesh or lambda discretization. The more intervals we have, the better the approximation will be. With this approximation of lambda, we know from the duality theory that the dual problem is a concave and non-smooth problem. And it's good that it is concave so that any maximum we found we know is going to be a global one. But since it is non-smooth, we will need to look for appropriate optimization methods. Popular methods in the non-smooth optimization theory are subgradient and bundle type methods, and they use the subgradient to determine the direction of ascension of the function. And there is a theorem that provides the expression of the subgradient of the dual function, and its components corresponding to each component of lambda is given in 10. And here you see the HJB equation in 11, 12, and 13. Which is associated to the dual function theta of lambda for each given lambda. And this is a first-order nonlinear partial differential equation, and upon solving it, we can compute the optimal path, starting from the initial point x0, and we compute the optimal path x star forward in time using the dynamics of the dual problem, the relaxed problem. And we determine the controls at each point in time by minimizing this Hamiltonian in 13. Now, once we find the solution of the dual problem, it will not in general be in the admissible set of the primal problem. This happens because we solve the problem numerically and we also approximate lambda with piecewise constant functions. So there will be a violation of this constraint where the virtual water should be equal to the real water. We devise a heuristic procedure to compute the primal admissible solution. and it goes like this. We modify the Hamiltonian of the dual problem by substituting back, instead of this virtual water, the real water released from an upstream dam in the past. We compute the primal admissible path x tilde forward in time using the dynamics of the primal problem, the initial original problem, and determine the admissible controls by minimizing this modified Hamiltonian. And now in this case, since we're moving forward in time, these terms that seem to be depending on the past will not be a problem for us because they are not even controls at time t. They are inputs because we have computed them at previous time steps. Another problem that we face is that the controls that we compute may not be smooth enough for the operator to implement them in practice. So to smoothen the controls, we will do the following. We add the H1 semi-norm of the controls to penalize large variations of the controls. This can be seen as regularization of our initial value function, and these coefficients beta can be seen as Tikhonov regularization parameters. And again, since we have the derivatives in the value function, we cannot directly associate an HJB equation to this function to solve the problem. So what we do is the following procedure. We first approximate the derivatives of the controls with finite differences, like this. And we modify the Hamiltonian of the primal admissible problem by adding the penalization of these derivatives into the controls, of the controls into the Hamiltonian, like these red terms over here. And again, these terms that seem to be depending on the past will just be input that we have computed at the previous point in time. We compute the primal smoothed admissible path x bar forward in time using the dynamics of the primal problem and determining admissible controls by minimizing this modified Hamiltonian. And by varying beta, we will be able to get different paths of controls, so with different level of smoothness. And there is a way, for example, an L-curve approach, which can help us to choose these beta parameters in somehow an optimal way. And I will describe it later. Okay, now we have computed the dual problem solution data and found some suboptimal smooth solution C of the primal problem. And we ask, is there a way to estimate the accuracy of our solution? So first of all, from the duality theory, we know that the dual problem in blue, the true dual solution, is a lower bound of the true primal solution in red. And this is the dual gap star, the quantity that we want to estimate. We know that we compute the suboptimal solution of the primal problem. So suboptimal solution of the minimization problem, which means this will be an upper bound for the true primal solution. And then when we compute the dual solution, we approximate lambda with piecewise constant functions. So we know it will be a suboptimal solution of a maximization problem, which means it will give us a lower bound on the dual solution. Therefore, this dual gap for given lambda that we will estimate will give us an upper bound of the true dual gap. And then also keep in mind that this primal in orange and this dual in green are the theoretical quantities that we do not have direct access to. We only estimate them numerically. So as long as we control the numerical errors in the procedure, we control the dual gap. So we can put an upper bound on the true dual gap, which consists of the numerical dual gap that we measure and the sum of the errors introduced in the procedure. Okay, now I would like to tell you about the algorithm that we are solving, that we're using to solve this problem. It consists of three main blocks and is organized as follows. So first we choose the lambda discretization, the refinement of lambda, and initialize it with lambda 0. We solve the HJB equation with given lambda and obtain our evaluation of the dual function theta and the corresponding subgradient xi. We then pass this information into the dual optimizer, where we compute the next iteration of lambda using the limited memory bundle method. We pass this lambda back into the HJB, and then we go through this loop for a fixed number of iterations. And once we're out, we can compute the primal smooth solution and the corresponding duality gap. If we're satisfied with the tolerance we set on the duality gap, we stop. If not, we go back, we refine lambda further and repeat the procedure. And now I will talk in more details about each of these blocks. The first, we will look at the numerical solution of the HJB equation, and we employ the backward in time upwind finite difference for the HJB equation, which has been shown in the literature to converge if the scheme is monotone, consistent, and stable. And the condition that ensures stability is known as the CFL condition, and it is given in 21. And it so happens that the same condition is enough to ensure the monotonicity of the Hamiltonian. In the upwind finite difference scheme, we have two options to approximate the spatial derivatives with: the upwind derivative d plus and the downwind derivative d minus. And which one we choose at each point depends on the value of the drift term for each of the power sources in the system. Once we solve the HJB equation and store all the derivatives of the value function at all points of the grid, we can compute the optimal path x star and the corresponding controls phi star by minimizing the Hamiltonian of the dual problem forward in time and interpolating the derivatives linearly at points off of the numerical grid. The dual cost will be the cost over the optimal path, and the subgradient will be the value of this constraint violation over the optimal path. By the end of this step, we will have the dual cost and the corresponding subgradient, which we pass to the optimizer. So how are we going to optimize the dual function, which is a concave and non-smooth function? So I mentioned that many popular methods use the subgradient to optimize the non-smooth function. And the subgradient is the generalization of the notion of gradient for non-differentiable functions. And formally, it is defined as all vectors that satisfy this relation in 28. So for example, in the one-dimensional case, where we have the function theta of lambda with a kink at lambda 0. And the subgradient at this point will be equal to the slope of all the lines passing through this point and lying completely above the curve theta of lambda. At all points where the gradient is defined, the subgradient is equal to the gradient. And we will be using one of the subgradient methods in our optimization. The dimension of our optimization problem depends on our refinement of lambda. So recall that we approximate lambda with piecewise constant functions, and the number of intervals over here is something that we can choose. So the more intervals we have, the better approximation of lambda we will have. But on the other hand, we also increase the dimension of optimization problem. And in our work, we've chosen the following approach. We start with the coarsest level of discretization, and then we keep refining lambda and keep increasing the dimension of a problem until we get the dual gap that we are satisfied with. The following theorem provides the necessary and sufficient conditions for a concave non-smooth function to attain its global maximum. And the conditions are that either we have 0 in the subdifferential or that the function is non-decreasing in any direction d. The popular methods, the subgradient and the bundle methods, differ in the following way. So the subgradient methods use only the single subgradient to compute the next step. And the bundle methods accumulate information about subgradients over a number of iterations and use them to create a piecewise linear approximation of a function at a given point. And these methods are much more complicated, but they converge much faster. And the method that we use, the limited memory bundle method, is of a bundle type. And by the end of the loop, we will have found the optimal solution for a given approximation of lambda. And now, before we can compute the dual gap, we need to compute the primal smoothed solution. And before that, we need to choose these coefficients beta in an optimal way. We penalize controls and tune these parameters separately for different types of controls, and I will explain how we do it using the battery controls as the example. So first we compute the primal cost C bar and the variation term, this variation of the controls over the path, V, separately for a set of values of beta. Then we plot this variation term V over the x-axis and the cost over the y-axis, C bar. And what we will have is this kind of L-shaped curve. The points on the far right of this curve correspond to the smallest values of beta, where the controls are not yet smoothed, and they are very close to the optimal path. And as we start increasing beta, the variation term will decrease because the controls will become smoother. But since we are moving away from the optimal path, at some point the cost will start to increase. And once we have plotted these terms as we do on this plot, it is easy to see which values of beta will give us the best results. This will be the values that are as smooth as possible without increasing the cost too much. And now, after computing the primal smoothed cost, we can compute the dual gap and decide if we reach the desired tolerance level or we need to go back, refine our approximation of lambda and repeat. Now, I would like to show you the results that we have using our algorithm and the real data from Uruguay. So here you see the slices of the value function plotted against time and all of the special variables that we have. And you can notice that many of them look piecewise linear, except for this plot, which corresponds to DAM4. This suggests that in principle, we can use an ansatz to approximate the dependence of the value function on all of these nicely behaving variables and reduce the dimension of our problem. Then we can calibrate the parameters of these ansatz by using the available data. Now have a look at the controls. In the first row, you see the turbine flow, and on the second row, the spillage. The first column is the optimal controls, the middle column is the admissible controls, and the last one is the smooth controls. And the thing to notice here is that the controls look quite complicated and unpredictable. And this is a good point where I can explain how our continuous time approach is advantageous to the discrete time one. So suppose that you have computed these controls using a discrete time approach with a time step in the schedule of 1 hour. And suppose that now you want to have a schedule with a better resolution. What you will have to do is you will have to recompute the whole problem because it's difficult to expect that you can have good results from interpolating these unpredictable controls. But in our approach, we compute these controls using the very nicely behaving value function. And it is more reasonable to expect that we can use the derivatives of these smooth functions and have a good interpolation of the controls from that. Another thing to notice here is these smoothed paths, which look actually visibly smoother than the controls over the admissible path. And here are the controls of the battery. Again, the optimal controls, the admissible controls, and the smoothed controls. And the effects of the smoothing can be seen especially well in this case, because this regime of operating the battery is much more attractive for the operator, where you can just turn the battery on a little in the beginning and then essentially turn it off, as long as this does not increase the cost of power production too much, which is our case. In the lower row, you see the virtual controls over here, and the discrepancy between the virtual water and the real water. And you can see that in our problem, we still have some discrepancy, but since we have reached the desired duality gap, we are satisfied with this solution. Otherwise, this type of plots can be used to suggest a non-uniform discretization of lambda, where we could, in principle, approximate lambda with one constant on this big time interval. We can approximate on this small interval with a different lambda and then a different lambda over here. And here you see the power production profile, where you see how the power is generated with each of the power sources in the system. And on the left, it is the optimal power, the power production over the optimal path, and on the right, over the smoothed path. And here is an example of the surface of the dual function. This is plotted in the simplest case where both lambdas are constant, just constant throughout the whole interval. And this is the case where we can plot this two-dimensional surface. And this is a good illustration of why the optimization is complicated, because we have kinks in both directions of the function, and we never actually reach the zero value of the subgradient. Whenever we are reaching the optimum, the subgradient will start jumping from one. The algorithm gives us the jumps from one side to another, and this happens in every dimension. So the higher dimensional problem we have, the even more difficult optimization will be. And here are the results of the optimization. We had the relative duality gap of 9% on the first level of lambda refinement. And on the second level, we already reached 1%. And such good results have been obtained with a very efficient optimization method, the limited memory bundle method. And with that, I would like to conclude my talk and mention some of the directions of further research. So first thing which we are currently working on now is incorporating the stochastic modeling of the wind and solar power, which results in a stochastic optimal control problem. And the most difficult part in it is the optimization of the stochastic dual function. And we've been trying different optimization methods, and this is quite a difficult task, I should say. Another direction that we can go with is the reduction of dimensionality of the HJB equation, if we propose a suitable ansatz for the dependence of the value function on all those dimensions except for DAM4. And we also use the Markovian projection to merge all the stochastic processes that we have in the system, the wind, the solar power, the demand, because as you've seen, we already have 5 dimensions in our deterministic problem, so we cannot afford to enlarge the space too much. Thank you for your attention.
Thank you very much, Eliza, for this nice talk.